All right, welcome. In this explainer, we're going to put on our detective hats. We're going to become data detectives. Our whole mission is to look at a scene that's just full of raw clues, like a spreadsheet, and learn the techniques to piece it all together and find the real story hiding inside. So let's get right to it. Every great investigation kicks off with one big question. So picture this. You're looking at a case file. You've got two main suspects, or in our world, two variables. And you start to notice this suspicious pattern. Whenever one of them shows up, the other is never far away. They definitely seem connected. But how? What is the real story going on here? That's the question that's going to drive everything we do. Now, the official fancy term for this kind of detective work is bivariate analysis. I know, it sounds a little academic, but the idea behind it is actually super simple. All we're doing is looking at two variables, our two persons of interest, at the exact same time. We're just watching how they behave, how they interact, to see if we can find a plot. Are they in cahoots? Does one make the other one act? This is where the story really starts to come together. Okay, before we go any further, we've got to talk about the number one trap. This is the biggest, most common mistake a rookie detective makes the second they spot a pattern. And believe me, getting this wrong will send you down a completely false trail and have you accusing a totally innocent suspect. So let's look at the evidence file. Fact number one that we observe is simple. It's clear. The data shows that as ice cream sales start to go up, a second, much more tragic pattern shows up right alongside it. The number of drowning incidents also increases. When one rises, the other rises. The connection, it seems undeniable, right? So the rookie detective, staring at this crystal clear pattern, asks what seems like the obvious next question. Is there a direct link? Does eating ice cream somehow cause people to drown? I know, it sounds totally absurd when you say it out loud, but the data pattern is sitting right there in front of you. The answer is a hard, definite no. That conclusion is just flat out wrong, and falling for this illusion is the rookie's single biggest mistake. And this brings us to the golden rule, the master-level principle that separates the amateurs from the expert investigators. You have to burn this into your brain. Correlation is not causation. Just because two things move together does not, and I repeat, does not mean one causes the other. This is probably the most important warning in all of data analysis. Okay, so if the ice cream isn't the bad guy, then what in the world is going on? Well, the master detective knows to look for a hidden character, right? A third party that's secretly influencing the whole scene. In our world, this is called a confounding variable. It's this unseen force that's pulling the strings on both of our suspects, making it look like they have a direct relationship when they don't. So in our case, the confounding variable, the real culprit, is just hot weather. The summer heat makes more people want to buy ice cream. Of course, it also makes more people go swimming, which tragically is what increases the chances of drowning incidents. The ice cream is completely innocent. It was just in the wrong place at the wrong time, connected only because it was also influenced by the real cause. All right, so we know not to jump to conclusions about cause and effect. That's lesson number one. But how does a professional detective actually measure the strength of a connection between two variables? How do we put a number on that initial pattern we spotted? Well, let's open up the professional's dossier and check out the tools of the trade. We've got two main tools here, covariance and correlation. The best way to think about this is that covariance is like the detective's first hunch. It points you in the right direction. Do our suspects move together or in opposite directions? But the number it gives you is kind of weird and hard to interpret on its own. Correlation, on the other hand, now that is the certified report. It takes that hunch and turns it into a standardized, precise score, always between -1 and +1. And this score is so powerful because it tells you both the direction and the strength of the relationship in one clean, easy-to-read number. And here's how you read that certified report. A score of +1 means our variables are in perfect sync. When one goes up, the other goes up by a totally predictable amount. A -1 means they're perfect opposites. And a 0, well, that means there's no real linear connection between them at all. As a general rule of thumb, anything around 0.7, positive or negative, is considered a pretty strong relationship. Definitely one worth looking into more. So now we can spot a relationship and we can even measure how strong it is. But what happens after we've done all our homework? What if we've ruled out all the confounding variables and we have a really strong reason to suspect that one variable actually does cause the other? Well, at this advanced stage, we can go from just looking at the past to actually predicting the future. And this is an absolutely crucial point. We only move on to this next step when we are pretty darn sure a real causal link exists. This next tool isn't for finding correlation. It's for modeling a cause and effect relationship that we already suspect is there so we can make some educated guesses about what's next. The tool for the job is called linear regression. At its heart, it's just a formula we build to predict an outcome. We call that our dependent variable, or y, based on some factor we think is causing it, our independent variable, or x. The model basically draws a straight line to represent that relationship, and it uses that classic equation you might remember from school, y equals mx plus c. Let's break that down real quick. Imagine y is the outcome we want to predict, say our total sales for the month, and x is the factor we control, maybe our advertising budget. C, the intercept, is our starting point. It's our baseline sales if we spent $0 on ads. But the really important part is m, the slope. That number tells us exactly how much our sales, y, are predicted to go up for every single dollar we add to our ad budget, x. It puts a number on the impact. But, how good is our prediction? Is it reliable? That's where R squared comes in. You can think of it as an accuracy score for our model, from 0 to 1. So in our example, an R squared of, say, 0.85 would mean that 85% of the changes in our sales can be explained by our advertising budget. The other 15% is just other stuff. It's a really clear way to see how much of the story our model is actually telling.
So the big takeaway here, the whole point, is to move beyond just looking at what happened and start predicting what will happen. We're building a formula, a predictive profile that lets us say, hey, if we change this input X, we can pretty reliably forecast what's going to happen to our outcome Y. It's a huge leap from just analysis to actual forecasting.
And there you have it. You now understand the core investigative techniques of a data detective. You know how to spot a pattern, how to sidestep that huge trap of confusing correlation with causation, and you even know how to model a relationship to predict what's coming next. You've got the framework. But to actually get your hands dirty and perform these investigations, you need the right toolkit. In our next explainer, we're going to open up that toolkit and look at the specific Excel functions that really bring all these techniques to life. But for now, I'll just leave you with this question to chew on. Think about the data all around you, at your job, in your hobbies. Now that you're armed with these ideas, what hidden stories are just sitting there waiting for a detective like you to come along and uncover them?